Welcome back, my dear friend. Get comfortable and let go of today's stress. You've done a great job. Now it's time to relax. Let's gently move into today's topic. Have you ever wondered, why is the sky blue? Why is grass green? And what even is color? At first glance, these might seem like childish questions, the kind kids ask while staring out the window or collecting leaves in the park. But behind them lie deep mysteries of perception, physics, and even philosophy. Why do we see the world the way we do? Why does the sky seem blue on a clear day, and the grass beneath our feet green? Where do these colors come from? And do we all see them the same way? What I want to say is, color isn't just reflected light. It's not an objective feature of an object. Color is a sensation, an experience that happens in our mind. It emerges at the intersection of light, eye, and brain, transforming electromagnetic waves into vibrant blues, warm yellows, and deep greens. Color affects everything, from the groceries we buy to how we perceive other people's faces. It can calm us or make us anxious, inspire or irritate. Colors set the mood of paintings, give meaning to logos, bring life to clothing, and carry deep symbolism in flags and rituals. And color is subjective. The same shade can appear different under different lighting. It can be seen differently depending on culture, language, or even the structure of a person's retina. This makes color not just a physical phenomenon, but a deeply human one. To understand the nature of color is to touch the mystery of how our perception works. It's a story about light in the eye, about the brain and illusions, about how physics becomes emotion. In this video, we'll explore that path, from rainbows to photosynthesis, from optical illusions to philosophical questions. Because color isn't just what we see, it's how we see. Let's take a closer look at what color is from a scientific point of view. Scientifically speaking, color isn't a property of the object itself. It's the result of how light interacts with our vision and our brain. Put simply, color is a sensation, a subjective interpretation that our brain creates in response to light of certain wavelengths. Light is a form of electromagnetic radiation that travels in waves. Different types of waves have different lengths and, therefore, different energy levels. The full electromagnetic spectrum ranges from radio waves to gamma rays. But the human eye can only detect a narrow band, roughly from 380 nanometers, which is violet, to 750 nanometers, which is red. That narrow band is what we call visible light. Short wavelengths, around 400 nanometers, appear violet or blue. Medium wavelengths, about 500 to 600 nanometers, appear green or yellow. Long wavelengths, around 700 nanometers, appear orange or red. So, colors don't live in the objects themselves, they live in the light. One of the key ideas in the science of color is this. Color isn't what the object is, it's how it interacts with light. When white light, like sunlight, hits an object, some wavelengths are absorbed by the surface, and others are reflected. The reflected wavelengths are what reach our eyes. And that's what creates the experience of color. For example, a blade of grass absorbs red and blue wavelengths and reflects green, so we see it as green. Charcoal absorbs nearly all light, so we see it as black. A sheet of white paper reflects almost all wavelengths, and that's why it appears white. That's how we see. Prism and the proof that color is in light. When white light passes through a prism, it splits into a spectrum, a rainbow. This happens because waves of different lengths refract, that is, change direction, at different angles. For example, violet waves refract more strongly, while red waves refract less. This phenomenon is called dispersion, and it proves that white light is made up of many colors, not the other way around. It was Isaac Newton in the 17th century who experimentally showed that colors already exist in the light. and do not appear in the prism. The prism only separates them. Moreover, if you gather the split light back together using a second prism, you get white light again, confirming that the colors are hidden inside the white light. Again, color is perception, not an object. It is important to emphasize, objects do not have color in an absolute sense. They only reflect certain wavelengths, and our brain interprets this information as a specific color. That is why in the dark, where there is no light, all colors disappear. Because without reflected light, there is no signal for perception. All these scientific statements can be explained with one simple formula. Physics of light plus psychology of perception equals color. So, color from a scientific point of view is a meeting of physics and neuroscience. It is born from waves of electromagnetic radiation, through interaction of light with objects, and finally turns into a sensation inside the brain. Therefore, we can say, color does not exist in the external world by itself. It exists only at the moment of perception, in our eyes, in our head. We've established that when we look at the world around us, we don't actually perceive the objects themselves. We perceive the light reflected from them. This light enters the eye, passes through the cornea and lens, bends, refracts, and focuses on the retina, a thin, light-sensitive tissue at the back of the eye. This is where the magic of color perception begins. On the retina, there are two types of photoreceptors, rods and cones. Rods are extremely sensitive to light and allow us to see in low light conditions, like at night. However, they have no color sensitivity. That's why at night we mostly see the world in shades of gray. Cones, on the other hand, work only when there is enough light, but they enable us to distinguish colors. There are three types of cones. Some respond primarily to long wavelengths, which is red light, others to medium wavelengths, which is green, and the third type to short wavelengths, which is blue. All the colors we see are the result of a combination of signals from these three types of cones. For example, if the green and red cones are both stimulated at the same time, the brain interprets this as the color yellow. This principle is called trichromatic. Three channels of color perception create the whole rainbow of sensations. Color perception is not just biology. It's also interpretation. Our brain doesn't just passively receive signals. It actively guesses what we see. Lighting, background, neighboring colors, the context of the scene. All of these affect how we perceive the same color. For example, a white sheet of paper looks white both in sunlight and in shade, even though in the shade it reflects much less light. This phenomenon is called color constancy, the brain's ability to correct color depending on lighting conditions. Moreover, everyone's color perception can differ. Genetics, age, eye health, all affect the sensitivity of photoreceptors. Even among healthy people, there can be slight shifts. What one person sees as pure blue might look bluish-green to another. Sometimes this leads to surprising effects, like the famous dress that some people saw as white and gold, while others saw it as blue and black. This is not magic, but an example of how differently the brain can interpret color depending on assumptions about lighting. By the way, we'll talk a bit more about the dress later. So, our experience of color is a complex collaboration between the eyes and the brain. We don't just see color, we construct it. And every time you look at a sunset, a rainbow, or your favorite painting, a delicate and almost magical processing of signals happens, turning physical light into sensory perception. So, the story of the dress is one of the most vivid and memorable cases showing that color is not an objective property of an object, but the result of interpretation made by our brain. How did it all start? In February 2015, a user posted a photo of a dress online, asking friends, "What color is it? Blue and black, or white and gold?" And the internet literally exploded. Millions of people couldn't agree. Some were 100% sure the dress was white and gold. Others were just as sure it was blue and black. What's going on here? This is a showdown of neuroscience versus pixels. If you look at the image in a graphic editor, you can check. The pixels are actually closer to blue and brown shades. But the brain is not a computer. It doesn't just perceive colors as they are, it interprets information depending on the conditions. One of the main conditions is lighting, and that's where the whole point lies. Why does the brain adjust for lighting? Our brain always tries to compensate for lighting to maintain stable color perception. This phenomenon is called color constancy. For example, an apple stays red both in daylight and under incandescent light, even though the reflected wavelengths are physically different. When we look at an ambiguous image without clear light sources or shadows, the brain has to guess the lighting conditions. Here are two scenarios. First, if your brain decides the dress is in shadow or under cool lighting, like blue light, it removes that cool tint, and you see the dress as white and gold. Second, if the brain thinks the dress is lit by warm light, yellowish, it neutralizes that warm tint, and you see blue and black. So, different guessed lighting conditions lead to different perceptions of the same pixels. Why do people see it differently? This is a unique example of how individual our perception is. It depends on experience. For example, you might be used to certain types of lighting, biological factors, differences in vision and cone cell activity, context, and even time of day. The brain processes visual information differently in the morning and evening. What does this prove? The dress effect became an important illustration for scientists studying perception. It proved that we don't see reality as it is, but rather the brain's assumptions about what it should be. Color is a dynamic, subjective process depending on context, light, and interpretation. The most interesting thing is that the dress really was blue and black. Later, it became known that in reality, the dress is blue and black. But this doesn't invalidate that millions of people honestly saw it as white and gold. This is not a vision error, it's a feature of how the brain works. The dress case is modern classic perception. It shows that even in the digital age, when pixels are measurable and objective, perception remains subjective. Our brain is not a camera. It doesn't just record an image. It actively constructs what we see. That's why the same object can create different color experiences for people, and none of them is wrong. Let's get back to the main question. So, why is the sky blue? Sometimes the simplest, everyday things hide surprisingly complex science behind them. Take the sky, for example. We look at it every day, in the morning, noon, evening, and usually take its blueness for granted. But why is it blue exactly? At first glance, sunlight seems white, but in reality, it consists of many colors, all the ones we see in a rainbow. It's a mixture of waves of different lengths. Short waves, violet and blue. Long waves, orange and red. When white light passes through a prism, it splits into these components. The prism is basically a simplified model of the atmosphere. The thing is, the atmosphere acts like a giant diffuser. Our planet is surrounded by a thin but powerful layer, the atmosphere, made up of molecules of oxygen, nitrogen, water vapor, and many other particles. When sunlight enters the atmosphere, its waves collide with these molecules. And here comes the phenomenon called Rayleigh scattering. What is Rayleigh scattering? It's a physical phenomenon where short wavelengths, like blue and violet, scatter in many directions much more effectively than long wavelengths, red and orange. Imagine each beam of light is like a tiny arrow. The short arrows are easier to knock off course when they hit air molecules. The long ones fly almost straight. So why isn't the sky violet? Good question. Violet light actually scatters even more than blue. However, First, our eyes are more sensitive to blue than to violet. Second, there is less violet light in sunlight than blue. And third, some violet light is filtered by the upper layers of the atmosphere, including the ozone layer. As a result, our brain interprets the sky as blue, a balance between blue scattering and our visual capabilities. Why are sunsets and sunrises so bright and colorful? When the sun lowers to the horizon, its light passes through a much thicker layer of the atmosphere. This means the short waves, like blue, violet, are scattered out completely before reaching our eyes, and mostly long waves, like red, orange, yellow, get through. That's why sunsets and sunrises are painted in warm, fiery colors. And why are clouds white? Clouds consist of tiny droplets of water and ice crystals. They scatter the entire spectrum of wavelengths roughly equally. This is called non-selective scattering, or Mie scattering. When all colors scatter evenly and reach our eyes, we see white. That's why clouds are usually white or grayish, regardless of the time of day, but not blue. What does this tell us about perception? The scientific view of the sky's color reminds us that how we see the world depends not only on the properties of light but also on the features of our vision. That is, the sky is blue because light interacts with the atmosphere in a certain way, and our eyes choose the interpretation they understand best. A small conclusion and a big wonder. Every time you look up at the sky, you witness in action physics of light, chemistry of the atmosphere, biology of vision, and the magic of human perception. And all this, just so you can say, what a beautiful blue day today. Alright, now that we've covered the sky, what about grass? So, why is grass green? At first glance, it seems simple. Grass is green because it looks green. But behind this obvious fact lies an amazing biochemical and evolutionary story involving one of the most important pigments on the planet, chlorophyll. For plants, sunlight isn't just a source of light, it's a source of life. They can convert solar energy into chemical energy through a process called photosynthesis. This is a complex chain of reactions where chlorophyll plays the leading role. What does chlorophyll do? Chlorophyll is a green pigment found inside plant cells, in structures called chloroplasts. It has a unique property. It absorbs light mostly in the red and blue parts of the spectrum, where photon energy is perfect for photosynthesis, but it's poor at absorbing green light, which it mostly reflects, and that reflected green light is what our eyes see. That's why grass, leaves, and most plants look green to us. We see the light the plant filters out and sends back into the world. The evolutionary advantage of green. You might ask, if green light isn't used, why haven't plants evolved to absorb it too? One hypothesis suggests that early photosynthetic organisms evolved in environments where green light was less available, like underwater. Evolution locked in efficiency in the red and blue ranges, leaving green light mostly unused. Also, reflecting green light helps plants avoid overheating, acting like a natural sunshade from excessive sunlight. Why did grass and leaves change color in autumn? Green dominates during the warm seasons when chlorophyll production is active. But when autumn comes and temperatures drop, plants start preparing for winter. Chlorophyll synthesis slows and stops. Existing chlorophyll breaks down and disappears from cells. Other pigments, always present but hidden under green, come forward. Carotenoids, responsible for yellow and orange hues, and anthocyanins, which create red and burgundy colors and protect the plant from oxidative stress and cold. Color is a sign of life. When you look at a green field, lawn, or forest, you're actually witnessing a massive biological system converting energy, working live and in real time. The green color of grass signals photosynthesis is happening here. Life is happening here. So grass is green not just because nature thought so. It's because its cells reflect excess light that isn't used for food. This reflection isn't a side effect. It's a sign the plant is alive, working, turning sunlight into life on Earth. Next time you walk in a park or look out the window at a green lawn, remember, you're not just seeing color. You're seeing a living solar energy factory. When we talk about color, we often think of it as something universal. Red is red, green is green. But what if that red to one person looks just like green to someone else? Welcome to the world of color blindness, a condition where color vision works differently. What is color blindness? Scientifically, our color vision depends on 3 types of cone cells in the eye, each sensitive to red, green, or blue wavelengths. For people with color blindness, one type of cone might be missing, or it might not work properly. That doesn't mean they see the world in black and white. That's very rare, called a chromatopsia. Most colorblind people see colors but confuse some of them, especially in certain lighting or backgrounds. The 3 most common types. 1. Protanopia. No sensitivity to red light. Red shades may look darker or blend with green and brown. 2. Deuteranopia. Trouble perceiving green. Green and red tones are often confused, especially together. 3. Tritanopia. A rare type affecting blue and yellow perception. Blue might look greenish, and yellow might appear pinkish or faded. What does the world look like to a colorblind person? Trying to imagine it is like explaining the taste of strawberries to someone who's never eaten anything sweet. Color is a subjective experience created not in the eye but in the brain. So even the best color blindness simulators can't fully capture what it's like living with it every day. Important to know, color blindness isn't a defect, it's just a difference. About 1 in 12 men and 1 in 200 women worldwide have some form of color blindness. For many, it's not a big problem, just a different way of seeing the world. Fun fact, some colorblind people are professional artists, designers, doctors, and soldiers. They develop alternative ways to recognize things, relying on shapes, textures, and context, not just color. Are there tools and tech to help? Yes! Special glasses and filters like Enchroma or Pilestone don't cure color blindness but can enhance color contrast, helping people distinguish hues better. Also, web and UI designers create accessible interfaces. Color coding and labels are used more often. Many devices now include color-blind-friendly modes. Can we translate the experience of color? Trying to explain red to someone colorblind is like explaining music to a deaf person. You can describe it with words like warm, energetic, or intense, but the sensory experience itself is unique. Still, talking about color blindness opens our eyes to how relative and personal perception really is. Color blindness reminds us that reality isn't the same for everyone. We all look at the same sunset, but see it in our own way. And that's not a flaw. It's the beauty of diversity. Let's talk about the most vivid symbol of color, flowers. We admire their beauty, but rarely stop to wonder, why are flowers so colorful? Actually, color is the language of plants. It's their way of saying, hey, there's nectar here, come over. Since plants can't move or shout, they use flowers to attract insects, birds, and other pollinators. Bright colors are like an advertisement. Here's an interesting fact. Bees, for example, barely see red, but they're great at seeing ultraviolet. Many flowers have UV signposts that guide bees right to the nectar. Some flowers look the same to us but appear completely different to insects. Why are flowers so different in color? It depends on pigments. Anthocyanins give blue and red shades, carotenoids create yellows and oranges, and flavonoids bring soft pastel tones. The pH inside petals can change the color of the same pigment. Anthocyanin can look blue or red depending on acidity. Even tiny cell structures affect shine and shimmer, creating optical illusions. Remember, flower colors aren't for us. They're for insects and birds. Bees love blue and violet. Birds see red really well, which bees mostly miss. And white. Fragrant night flowers attract moths. It's a whole evolved system of communication. But then humans came along and turned flowers into symbols of feelings. Red roses mean love. White lilies mean purity. Violets mean modesty. And chrysanthemums can mean life or mourning depending on culture. So flowers are both nature's language and our cultural code. When you look at a flower, remember, for a bee it's a signpost. For us it's beauty. And for the plant it's survival. Flowers are living messages encoded in color. And every time you admire a flower, you're not just seeing beauty. You're seeing life's strategy in action. We're used to thinking of color as an objective property of the world. An apple is red, a lemon is yellow, grass is green. But pause for a moment. What is red without an eye to see it? Color isn't an inherent trait like hardness or mass. It's the result of an interaction between three things: light, an object, and an observer. Remove any one of these, and color disappears. In total darkness, where there are no photons, there's no red or blue. Where there's no observer to interpret light, there's no color. There are only wavelengths of the electromagnetic spectrum. When white light hits an object, some wavelengths are absorbed and others reflected. The reflected waves enter the eye, activating certain photoreceptors, and the brain translates this into a color sensation. But this translation isn't universal or absolute. It depends on the structure of the eye, the brain's wiring, the scene's context, prior experience, expectations, and even mood. This means what you see as blue might look a bit different to someone else. And for some creatures, that blue might not exist in the way you perceive it. Who sees differently? Color perception is an evolutionary trait shaped by each species' needs. Here are some fascinating examples that challenge our usual worldview. Bees see ultraviolet light but can't see red. Many flowers that look plain to us appear to bees as bright UV targets guiding them to pollen. Some snakes, like pythons and boas, can sense infrared radiation, essentially seeing heat. Their vision blends visual and thermal worlds. Mantis shrimps are underwater superheroes of vision. They have up to 12 types of photoreceptors. Humans have 3, perceiving a vast range of light, including UV and polarization. Strangely, their brains don't blend these colors into gradients like ours, but process each channel separately, likely for identifying surfaces, threats, and mates. Dogs are dichromats with 2 types of photoreceptors. They mainly see the world in blue and yellow tones, unable to distinguish red and green. But their vision is optimized for detecting motion and seeing in low light. Functional, not inferior. Philosophers ask, if a tree falls in a forest and no one hears it, did it make a sound? The same goes for color. If no one looks at a rainbow, does it have colors? Or is it just light waves of different lengths? The scientific answer: color is an inseparable part of perception, not the object. It doesn't live out there in the world, but here, in consciousness. It's an illusion necessary for survival, recognizing ripe fruit, danger signals, faces, and emotions. Color helps us navigate quickly, but its reality is operational, not absolute. What if we saw differently? Imagine having vision like a mantis shrimp, seeing light polarization, the infrared heat trail of your teacup, ultraviolet markings on flower petals. The world would look different. You'd live in another reality, even though everything around was the same. That's why color is not truth, but interpretation, and one of the most poetic examples of how the brain creates the world, not just reflects it. Color doesn't exist out there. It's born in here. It's not a property of objects, but an act of perception. And once we realize this, it's clear how subjective, diverse, and amazing our world really is. The sun isn't yellow. The grass isn't green. We just see it that way. And that is beautiful. Sometimes it's better to see something once than to hear about it 100 times, especially when it comes to color. Theory becomes truly clear when you look at a rainbow emerging from a simple prism or can't believe that two absolutely identical squares look like different colors. Why? Because your brain decides how the world should look, and sometimes it makes mistakes. Welcome to the amazing theater of visual perception, the prism and white light. A prism is a simple but magical tool. When white light, like sunlight, passes through it, it splits into a spectrum of colors, from violet to red. This phenomenon is called light dispersion. Why does it happen? Different wavelengths of light bend at different angles. Violet bends the most, red the least. As a result, we see a rainbow hidden inside ordinary white light. This proves colors live in light, not in objects themselves. Without light, there is no color. The prism experiment is almost like magic, but a magic that can be explained. Color illusions, tricks of the eye. Where does physics end and psychology begin? Right at the border of color illusions. Take, for example, the famous checker shadow illusion. Two squares on a checkerboard look light and dark, but in reality, they are exactly the same color. Why? Because the brain automatically takes into account assumed lighting and corrects colors, as if improving the picture. Another vivid illusion is color constancy. The color of the same object may look different if it's surrounded by different backgrounds. This explains why the famous internet dress drove people crazy. Color is not just physics, but perception in context. Try looking at the world through red, blue, or green filters, and you'll instantly see everything change. Some colors disappear, others become brighter. Why? Colored filters absorb certain wavelengths, letting only part of the spectrum through. This can simulate how a person with color blindness sees the world. There are even special glasses that imitate different types of color vision deficiencies, useful for designers, teachers, and anyone wanting to understand just how subjective color perception is. Another cool experiment is using ultraviolet or infrared cameras, which let you see what's hidden from the human eye. Thanks to these technologies, we can glimpse the world through the eyes of a bee or a snake. Why is this important? These simple demonstrations are not just fun, they shatter the illusion of objectivity. You see how easily your vision can be fooled. You realize that color is not a fact, but a sensation. You understand that your brain makes assumptions that might be far from reality. Color is not simply there or not there. It is born in the moment of perception. And when you spin a prism, squint at a color illusion, or put on strange glasses, you literally watch your brain at work. And maybe you start to understand not only the physics of light, but also yourself. So next time you see a rainbow or a strange color on a screen, remember, you are part of an experiment that lasts a lifetime. Color is not just light. It's a story about us. When we ask ourselves, why is the sky blue? Or why is the grass green? It seems like we're searching for a simple scientific answer. But in reality, we touch something deeper, a profound interaction between the outside world and our perception. Color is not something that exists outside of us, in the objects we see. Color is an experience that happens inside. Light reflects off surfaces, enters our eyes, excites certain photoreceptors, and only then, in the brain, is the sensation of color born. And this sensation can differ from person to person, situation to situation, species to species. We think we see the world as it is, but this whole process shows we see the world as our brain makes it. Color is an act of interpretation. Our brain constantly analyzes, compares, and draws conclusions. Sometimes it guesses, like with the color of the sky or leaves. Sometimes it errs, like with illusions or the famous case of the dress, which look like completely different colors to different people. Color is not an objective fact. It is a matter of perception, context, light, and expectation. The brain adjusts and completes the picture of the world to make it logical in each situation, even if that means repainting what we see. Color is a subjective world. See ultraviolet. Mantis shrimps perceive colors beyond our imagination. People with color blindness see things differently. The conclusion is obvious. Colors as we know them do not exist outside the observer. Every organism paints its own picture of the world, and color is one of the key strokes in this personal perception. What looks richly green to one may appear grayish-beige to another, and both will be right in their own experience. Color is a bridge between science and feeling. Color holds a power beyond physics. It affects mood, evokes emotions, shapes aesthetics. We use it in art, fashion, architecture, and psychology. We link colors with feelings. Red, passion; blue, calm; yellow, joy. Color is a universal language, but everyone speaks it in their own way. Color is an illusion worthy of respect. The world of color is an illusion, but a surprisingly stable and useful one. We live in this illusion every day without noticing how skillfully it works. Understanding its nature does not break the magic. It deepens and beautifies it. Just as shadow depends on light, color depends on perception. It is fragile, fluid, relative, and this relativity is its beauty. Maybe color is a way to see the universe within ourselves. We look for answers outside, but color repeatedly brings us inward, to our eyes, brain, emotions, and experience. It shows that reality is not simply there. It is constantly created by us, every moment, every glance, every shift of light. In the end, color is not something that is, but something that happens. It arises at the intersection of the physics of light and the psychology of perception. It cannot be objectively fixed, only subjectively felt. It is unique for every species, and even for every person. Understanding color is a step toward understanding how our consciousness works. And perhaps most importantly, color reminds us that the world does not just exist. It is perceived. And this perception makes it alive. So the next time you notice a sunset painting the sky in orange and pink tones, know this: you are not just watching the sunset. You are participating in its creation. Good night, dear friend. Sleep peacefully.